Good afternoon, everyone. Hopefully some of you, or hopefully all of you, or at least some of you might have seen the announcements I posted last night. So I'm just gonna talk about those announcements in the homework, just for a few minutes at the top. Okay. So, let's see. Let's go to the announcements first. All right, so the announcements were regarding homework one and grade school. So homework one on Canvas shows the due date of Sunday. But I typically like to give 1 week. And so submissions will be accepted until Wednesday. I said so in the announcement. Okay. So try to get it done by Sunday, but if you can't, no big deal. You still have until Wednesday to submit. Right. And the contents of the homework, the questions are something that we're going to go over today. Okay, so we'll discuss the examples, and so you'll be in good shape to get those done. Second part is, or not second part, second announcement is about Gradescope. That's one of the reasons I was delayed by a few days. Gradescope is a new addition to Cal Poly. We just purchased a license, and it's a grading app, not AI based or anything like that. It's just a grading app that allows us to grade online in a much faster, better, and efficient way using rubrics. Okay, so instead of like writing everything out by hand, like manually making markings and everything, we just do mouse clicks, and then we have our rubrics that are that are typed up, and so students can see exactly the points they have earned, and they can see exactly the points that they have lost and the reason why they lost it. So it also provides instant feedback in that sense. Okay. And the reason it's faster and efficient at our end is because once we set up, we can group all the student assignments. This is something that you can't see at your end, but at our end, at the instructor's end, we can group all the assignments and all the sub questions and questions as the case may be, and we can just make a note. So if it's the same error that is repeated, over like course of like 30 student submissions or 60 student submissions, we can just enter like one click and say, okay, this is missing or this is incorrect. So, and then it goes way faster. I hope that makes sense. Right. And so since I'm implementing Gradescope, the way it works at your end is not very different. At our end, we have to set up the assignment and we have to go through everything. But at your end, essentially, what students are going to do is they're going to upload their submissions in the same Canvas links. And then the secondary thing that students have to do is to match your submissions with the page numbers. So for instance, here I have homework one that is under Gradescope. And then you would click homework one, so it opens up like there. And Gradescope page is embedded directly in there. And all you're going to do is upload submission. Okay. This is the instructor end, and I cannot simulate the student's end, but essentially that's what you're going to do. You'll have a space, you click upload, and you upload your PDFs. And once you upload your PDF, you will see the instructor created outline. That is nothing but the points for the questions. And all the student has to do is you have to link the page in your assignment that contains those questions or the answers to those questions. There's a video guide that I've linked in the announcement. So just go through that. It's just a few minutes long. Doesn't take up too much of your time, and it's not too onerous. Okay. All you have to do is you upload your submission, and then you will see the instructor created questions. So if I have, let's say for quiz one, we have 10 questions. So I have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perhaps there might be sub questions, yes or no, maybe, maybe not. Then all you do is you select, let's say your assignment is 3 pages long. Click on page one, and then you just link the corresponding questions. Page one contains question number 1, 2, 3. Page two contains 4, 5, 6, 7. Page three contains 8, 9, 10. And that's it, done. Okay, so the student's end is not much more of an additional work that is required. Right. So go through the video guide, go through your submission, and then let me know if you have any questions. Yes. Yeah, so I was just going to talk about that next. So since I have implemented this, quiz 01 student submission has been created. And all I'm asking students to do is you take the same PDF that you had submitted already for quiz 01, you resubmit it in this place. Okay. So the student end, this is going to look like this. It shows you quiz 01 student submission due on October 3rd, which is, well, counting from last night, it's 3 days. But again, if you have the PDF, just go ahead and submit it anytime you have a few minutes. Shouldn't take more than, should take less than 5 minutes of your time. Probably not even that much. Okay, so just submit it there. And then once I have all of the submissions in there, then we'll begin grading. Sounds good? Okay, so again, quiz 01 student submission is simply a resubmission of the PDF that we already submitted on Monday. And then going forward, I'll delete all of the others. Everything will be just submitted while the grades go. And again, at the student's end, it's opaque. You don't have to worry about a thing. All you see is one student submission assignment in there, and you just upload. That's all. Okay. Yes.
The quiz one we submitted, what's the format is different than the format we're supposed to submit it in? So like.
So format, the question being asked is about the submission format. The answer is there is no difference. It's still a PDF. Students will just work normally as they are, whether they work on a electronic tablet or whether they use pen and paper or pencil and paper. You create your PDF. Once you have your PDF, you upload it in the link. And then all you have to do, the additional steps you have to do is rematch. And those matches, like if you have a single page containing all of your answers, all you're going to do is page 1 and you click on all the questions that I've marked. So questions 1, 2, 3, 4, 5, 6, 7, they're all on page 1 and that's it. So the system essentially is the instructor sets up a point for every single question that we want to grade. And at the student's end, all the students are doing is you're letting the system know, hey, this page contains this question or the answer to this question. That's all you're doing. Does that make sense? Right? And so when we sit down and we open up the grading, we click on that, okay, question 1 is here, and we start grading, and we just click, okay, all correct, full points. Something missing, -1, and then we have the reason in there. And then as we go along, after the first few student submissions are graded, we just go on clicking, and then it just goes faster. Okay, so it's a more efficient, more better way. Typically, we would just write in, oh, -1 here, -0.5, and then students may not know the reason why it is. But in this case, you will know exactly why points are being lost, right? So it's a win-win, at least as I see it, it's a win-win for all of us. Okay, all right, so now let's go to our slide. And this is where we stopped. Section 2 is here. Okay. So we stopped on this slide. All right. Okay, so I think when we ended this slide, I think there was a little bit of a rush. So just want to go over this again. Broadly classified, electrical circuits have components broadly classified into sources and loads. Sources are energy sources, meaning they supply energy, they supply power, and loads is anything that receives or consumes the energy. Right? Electrical energy is converted into any form or multiple forms. If a source supplies power, mathematically, we want to represent that with a minus sign. And if it receives power, then mathematically we represent with a plus sign. So the mathematical equation remains the same. P, electrical power, is the product of voltage and current. But if it's a source, the mathematical equation has a minus in front of it. And if it's a regular component that's receiving it, simply a plus sign in front of it. Okay. Total energy is the area under the curve for power, right? So total area under the curve, we cut it up into individual slices. So dot dt, integrate it over the entire time period, 0 to t, that gives us energy. I'm assuming you are all familiar with these equations from physics classes. Kind of rings a bell. Okay, right. So again, total energy is simply the area under the curve for power, meaning we integrate or sum up the power for a certain period of time, 0 to t. Power equation is P equals VI. Instantaneous power, meaning P of t. Power as a function of time, meaning at any given point in time, if you're analyzing a system, the equation still remains the same. Whether we are analyzing the system for a few seconds or over a few minutes or over a period of days, months, or years, at any given point in time, we can calculate the power that would be given by P of t, and it will still be product of the voltage and current at that point in time. So P of t is V of t times I of t. That is here. P of t times I of t. All right. Then I want to talk about electrical switch. An electrical switch is noted with these two symbols. This represents an open switch. This represents a closed switch. Okay. Open and closed. And now open and closed electrical switch, if we use a mechanical valve analogy, then it's the exact opposite. In a mechanical valve, let's say you have a pipe, fluid is passing through the pipe. If you want fluid flow, if you want to block the fluid flow, then the valve must be closed. So a mechanical valve is closed, it will block or not permit fluid flow. In order to permit fluid flow, the valve must be open. The electrical switch is exactly the opposite. Switch must be closed for electric current to flow through. And if you want to stop the flow of electric current, then we must open the switch. So when you open the switch, no current can flow through, meaning I is equal to 0. But now there could potentially be a electrical potential difference between the two ends of that open switch. And so voltage would be non-zero. I would be equal to 0 because there's no pathway for electrons to flow through, but there could exist a voltage across the two ends of that switch. So V could potentially be non-zero. Okay? Make sense? Conversely, if you have a closed switch, the closed switch will permit current flow. So current, if it's flowing, will be non-zero. It will have some value. But because both ends of the switch are connected together, now it's the same electrical node, and the voltage across the closed switch would be equal to 0. So V would be equal to 0. So in both cases, P equals VI. In both cases, either V, the voltage, or I, the current, is equal to 0. So in an ideal switch, the power consumed in the switch is equal to 0. Either consumed or lost. Again, the function of a switch is simply to provide a pathway. So if it's consuming power, if it's consuming energy, that means we are losing power or energy to that switch, which of course is not good. So in an ideal switch, we say that an ideal switch is non-energetic. Non-energetic means does not consume any energy. Okay, and that's what this non-energetic means. Okay, but that's only possible for ideal. Only for ideal. In real life, we have switches, we have manual switches, right? Those are kind of like digital or control switches, but we have the manual flip switches. And those switches might have resistance on the order of like milliohms, perhaps. Right? And that's as close to an ideal switch as possible, especially if it's gold plated. Many of the switches are gold plated because it's non-corrosive, it does not corrode, and it's an excellent conductor of electricity. So many of the components we use, there's a thin film of gold on top. So gold contact pads are very common in electrical devices. All right. So it might be like power loss in that switch might be like not even milliwatts, perhaps microwatts or less, completely negligible, right? Okay, let's see. Example problems in just a couple of slides. All right, so for our devices, we have our standard equations. For a resistor, we have V equals IR. For a inductor, we have inductor voltage equals L di over dt. And for a capacitor current I is C dV over dt. This is just a summary of the equations we have already looked at previously. And these are the fundamental equations that govern the operation of these three components. Okay, V equals IR, VL is equal to L di over dt, and IC, capacitor current, is C dV over dt. And power, of course, is always V times I. V equals IR and P equals VI. From these two equations, if we combine them, we can derive two more equations for power, either in terms of the current or in terms of the voltage. To be clear, these are simply shortcuts, right? If you have the resistance and you have the current, you could find the voltage and then calculate power, or you could take the shortcut and simply use I squared times R. Same thing with the voltage. If you have voltage and if you have resistance, you could calculate current I and then find power, or use a shortcut and use V squared over R. Remember, I stated this and I'll keep stating it. All of circuit analysis based on three laws and three principles and three equations. V equals IR, Ohm's law, KCL, and KVL. So this is derived from Ohm's law, right? These equations, again, just derived from Ohm's law by combining it with the power equation. So I should add the fourth one in there, which is the power equation. P is VI. Okay, so there are multiple techniques that we learn. All of those techniques are based only on these three: Ohm's law, KVL, and KCL. just allows us to take some shortcuts. Okay, I think there is a error in there. Should be Joule's law of heating by a resistive device carrying constant current. Electrical heaters, or actually this principle of resistance and current passing through a resistance, it converts electrical energy into thermal energy, meaning the electrical power coming through is dissipated as heat. And there are real life applications that we have used every single day of, well, I would say not every single day, but very often in real life. Right? You plug a heater into the wall, you now got a space heater. Put water in it, it's now a water heater. You put a vessel on it and cook, it's now a cooking stove. These are just three of the most common applications of electric heating. Any others that you can think of? Electric blanket, yes, that's a good one. I didn't even think of that. That's a very good one. If we ever do laundry and it runs on electric, well, there are gas dryers, but there are also electric dryers. Those are, again, same principle, electric dryers. Also, if you, sorry, air fryers. Yeah, air fryers. So air fryers, just a side note, is nothing but a oven. Okay, it's an electric oven. Electric oven has a coil at the bottom and at the top. Some ovens have it at the top too. But an air fryer just as a coil, like in like our cooking stuff or cooking ranges, and has a fan on top of that electric coil. So if you look underneath the air fryer, you can actually see that coil. There's no difference, and it's just air that's like, there's a fan that blows the heat down on top of your food that wants to be cooked. So air fryer, that's a good application. How about an electric iron, clothes iron? I haven't done much ironing recently. I just wear t-shirts most of the time. But if I ever have to go attend a formal event, I have a shirt, pants, then yeah, you gotta iron those. That's again electric heater. Yes. Hair dryer, that's a good one. Think of that. Hair dryers, yes. Hair dryer, which brings me the exact same operating principle. You got a heater, you have a fan behind it. You can dry your hair with it. You can dry, like you spill water on the carpet, which I seem to do all the time. You use a hair dryer to dry it up, or you can cook with it. I just realized that it's the same thing, right? You got a fan, you have a fan behind a heat source. It's just blowing heat in one direction. So, yeah. Anyway, so coming back mathematically, the total energy or the power would be I squared times R and the amount of time that you're running it, delta T. Okay. Sometimes engineering can get real boring while we are learning that. We'll be going to the technical weeds, so to speak, but science and technology is all around us in real life applications. It is just a matter of tying it to it. So, all right, some example calculations, and these are going to form a big chunk of your homework. Okay. So you have a device like this. Perhaps it's a heater. And if you read the rating right here, you can barely make out that it operates at a voltage of 12 volts and it has a power rating of 100 watts. So anytime we are not even looking at the question statement yet. Okay? We are simply looking at the information that is presented to us. So in this case, the information presented to us is in the form of an image. So anytime you're working with a problem, extract all the information that you can. And this information could be in the problem statement. It could be in the circuit diagram. It could be in any other image. It could also be in a graph or a chart that accompanies that problem. Okay. Sometimes graphs and charts, not sometimes. Graphs and charts must have the axes labels along with the units. So you have time. Typically, it would be marked as seconds. Sometimes it's marked with milliseconds and microseconds. If you don't pay attention, and inadvertently you might say 0.5 seconds where it was 0.5 milliseconds, you're off by a factor of 1,000. Okay, so always pay attention to detail. So extract information. In this case, my information I have is that the voltage is 12 volts and power is 100 watts. Anything else given to us? Not right now. When it comes to quantities, what other quantities are remaining? I and R. So even without looking at the problem statement, I can say that voltage V is given to me or given to us, and power P is given to us. Current I is unknown, and the resistance R is unknown. And now, since we know our equations, we can calculate I, or we can calculate R from V and P. Right? I from Ohm's law, and then power from the power equation. Sorry, resistance from the power equations. And so that's what's shown here. You can calculate current from there, and then you can apply Ohm's law to calculate R. Or if the question was just find the resistance, you can just do P equals V squared over R. Let's take a pause, think over that. Let me know if you have any questions. Does it make sense? Okay, all right. All right, then let's talk about battery capacity. How many of you know the capacity of the battery in your mobile devices? Every battery has a capacity, right? That's the total energy stored inside the battery. So every smartphone, well, every phone, every tablet, every laptop that has a battery has a spec. That spec will tell you the capacity of that battery. There are two websites that are really good about listing all the specs. You can, of course, go to the manufacturer's website, but there are a couple of websites called Phone Arena and GSM Arena. And you can pretty much look up any phone manufactured anywhere in the world, and it will have the detailed specs of every single thing about that device. It'll tell you the frequency spectrum it can run on. It can tell you, it will tell you all the features the device has, hardware as well as software. And then at the bottom end, it will tell you the battery capacity for your device. Okay. Typical smartphones have battery capacities ranging from 4,000 to 5,000 mAh, milliampere hours. Battery capacity is measured in ampere hours, and then the voltage that it operates on. So AH stands for ampere hour, and then voltage, of course. Okay. If you multiply this together, if you multiply current and voltage together, what do we get? Power. Unit for power is watts. So we get, you multiply this together, you get a watt hour. If you consume you consume 1,000 watts for 1 hour. Anyone know what this is called? Does it sound like a lot? It's a kilowatt hour, yes, but in real life, or at the consumer end, there is a non-technical term for this. So kilowatt hour is correct, absolutely correct. It is a 1 kilowatt hour. So 1 kilowatt hour. If you ever pay your electricity bill, or if you look at your electricity bill or anybody's electricity bill, it will tell you how many units of energy or power is consumed in 1 month or in a time period. And so this is considered as 1 unit of electrical power. 1 kilowatt hour. So if we consume or use up 1,000 watts for 1 hour, that is 1 unit of electricity. Again, tying it back into a real life example. If you can get hold of an electric bill, just take a look at it, and we can see what your power consumption is. Okay, so that's 1 unit of electricity. Phones and tablets, the typical current runs in milliamps. So the battery capacity is also provided in milliampere hour. So you have a phone or a tablet, or even a laptop. Oh, remind me, I have like a couple of laptop batteries somewhere, so I'll bring those in and I can actually have smartphone batteries too. I used to love having smartphones where you can simply open the back cover, replace the battery, have 100% charge in like 10 seconds. So I still have those batteries with me. Anyway, so phones and batteries, phones and tablets typically are rated for milliampere hour. And the voltage they run at is typically 3.7 volts. So they supply 3.7 volts into the device. As I said, typical smartphone batteries are between 4,000 to 5,000. There are some that go above 5,000. There are some long capacity devices that have like 6,000 mAh battery capacities. So those phones can last for a long time. 5,000 is very common nowadays. Okay. So quick question, if you have a device, or if you have a battery that has a capacity of 1,000 milliampere hours, runs at 5 volts, for instance, voltage is irrelevant at this point, and you connect, or a consumption requires 10 milliamps, how long can you run it? Someone says 100. Only one student says 100. Any other guesses or calculations?
Hours.
Hours. 20 hours? Why did you change your answer? You were right the first time. So you were right when you said 100 because that's fine, okay? You can take it, not to put you on the spot. I love it when students talk and converse. So the way we would, what I'm trying to show here is if we know the capacity of the battery and we know the current draw, then we can predict how long your battery will last. Obviously, current draw is not always constant. But if it's like, let's just say it's constant for now, right? Your power goes out, you have a portable battery bank, you connect your light to it, it pretty much is going to stay constant. Okay, voltage will match up, it's not going to change. What we need to know is the current draw. Okay, so if it's 10 milliamps, it lasts for 100 hours. If you've ever purchased a portable battery pack, right? It'll have a capacity. Some of them have a capacity listed right on top. If you purchase nowadays, there are like battery packs that you can buy for your homes. Okay. Anyone ever hear of the Tesla Powerwall? Right, it's become a ubiquitous term in recent times. Well, the Powerwall is nothing but a battery. It's a battery that can be mounted on the wall and it provides power, hence the name Powerwall. Sounds fancy, but it's not. It's just a battery. It's an inverter, converts DC to AC, so it can connect. It can supply AC power to your homes, but that's what it is. And you can buy portable battery packs now, ranging from all sizes, like small ones with like one AC power outlet to like 5, 6, 7, 8 power outlets. And you can run your entire refrigerator. You can run your entire home just buying these huge battery packs. Yes.
10 milliamps in that, or was that just?
Oh, 10 milliamps was just a random example. So if we know the current draw, then we can just write, yeah, 10 milliamps. So, but that's a good question. And also to your point earlier, if we have so most LED light bulbs are nowadays like 8 or 10 watts. So let's say it's a 10-watt light bulb, runs at 120 volts, right? So we can figure out what the current consumption is for that light bulb. And based on that, if we know if the power goes out and you plug in an LED light bulb into a portable battery pack, we can predict almost to a T how long it's going to last. You have all the equations in front of you. You have the wattage, you have the volts it runs at, you have the battery capacity. You can figure it out. And that's the point of homework 1. Okay. So that's what that is. So this example right here is just providing some numbers regarding a vehicle battery. Tells you it runs at 12 volts. That's pretty standard, by the way. Most car electrical systems run at 12 volts. And then the capacity is given as 70 ampere hours. Okay, 70 ampere hours. And so from the voltage and from the battery capacity of 70 ampere hours, we can calculate the total power or energy that is stored in there. Simply multiply it, we get 12 times 70, 840 watt hours. Okay, 840 watt hours. Now, if our heater device is consuming 100 watts, we can calculate exactly how long that heater is going to function, which is 8.4 hours. Make sense? We have power, which is power, voltage, current, and now we're just entering a fourth quantity in there, which is time, T. So U and then next U. Yes. Oh, that's just provided right here. So 100 watt was provided in the example initially. So it's just a random example from the device. Yes. So the question being asked is, can we take the 70 ampere hours and divide it directly by the amps? And the answer is yes, we could. We are given at 12, and so 840 divided by 8.3. Oh, sorry, not 840. 70 divided by 8.3. Do we get 8.4? Okay. Yep. Just an example, just to show students that it's all possible combinations. So we don't have to actually calculate it that way, which also would be the question to ask if we do this at the bottom. Let me finish making this point and then you can answer the question. So the question 4 is, how much power can this heater obtain? I mean, calculate power, P, right? Power P is V times I. And so you're trying to calculate, but it's simply V square over R. So we don't need to calculate I. So just different ways of solving the same problem. Yes. Oh, that was just provided. The provided information. Question being asked was, where did this come from? It was provided information. 12 volts and 70 ampere hours. Okay. But definitely review this slide. But the 4 quantities in here is power, voltage, current, and time. That's all it is. If we have if you have 2, voltage and current, we know the power consumption. So as I was saying, the LED light bulb example, right? So if you have LED light bulbs in your residences, lying around, or just unscrew it, and you can read on the side. All LED light bulbs are going to run at 120 volts, 120. But it'll tell you the wattage. Okay, 800 lumen light bulb, LED light bulb would consume about 8 watts. But that gives you the power that it's consuming, not how long it's going to last, right? But now when you plug it, you 8 watts, 120 volts, so you can calculate how much current it's going to draw. And then if you have a portable battery pack, you can perform a small experiment. Calculate how long it's going to last, right? And so you charge up a portable battery pack, like 100-watt battery pack or a 200, 300-watt battery pack, comes with a single AC power outlet. You plug that lamp in there, see how long it lasts before the battery runs out. Okay. All right. There's one final thing. There's actually 2 things we need to do, but time is running out. 7 minutes. Okay. So in this circuit, we have a 12-volt source connected to a 1.44 ohm load. So this is the load resistor. And up till now, we have just talked about how all wires and components and everything is ideal, right? But in real life, ideal wires do not exist. So those wires, especially depending on their length, will have some resistance. That resistance is typically very small, milliohms, and nothing that rises to the level of interference. But if we wish to calculate, then we'd account for that resistance. So if you're setting up this circuit, for a source, current always goes from minus to plus, goes its way around this, enters here, causes the voltage drop at this polarity. Current flows in this direction, causes voltage drop here and here, and here and here. Plus minus, plus minus. Now, how do we find the voltage across all 3 resistors? Well, we can apply KVL. So if we apply KVL, I can write 12 volts is divided across 3 resistances. So I'll say VR1 plus VR load plus the bottom resistor. I'm going to call that VR2. Okay, VR2. And then I can apply Ohm's law and express each one of these voltages in terms of the resistances. I can write 12 is equal to I times R1 plus I times R load plus I times R2. And then, of course, that's how we get that equation. Okay. So we still have about 4 minutes left. I want to talk about LT Spice right after this. Okay. We apply KVL first, then we apply Ohm's law, and then we calculate and combine. So one of the homework questions is regarding such a circuit. But this leads us into LT Spice. SPICE stands for Simulation Program with Integrated Circuit Emphasis. It is a program that was released in the early 1970s at UC Berkeley. It was a student project. The name of the student was Nagel. Last name was Nagel. And the advisor was Dr. Peterson. And that itself, the SPICE program, is the gold standard even to this day. 50 years later, it's still the gold standard in electrical circuit simulation. Okay. It was based on the Fortran language, and you had to type up everything, which is still, by the way, the best way to learn SPICE. Okay, you type everything, meaning you say, okay, this is node 1, and you're connecting resistors R1, R2, R3 at node 1, or resistor R1 is connected between node 1 and 2, resistor R2 is connected between node 1 and 3, power supply is connected between nodes 2 and ground, and you describe the circuit using words. Okay, so it's a great way of learning. And then SPICE was made open source. Okay. And so lots of companies, lots of people, lots of universities took SPICE, took the code, and came up with their own versions. And so one of the most convenient versions that is available now is offered by Linear Technologies. And Linear Technologies, I think, is now part of Analog Devices. And Linear Technologies came up with it, and they still made it available for free. And so their version is known as LT Spice. Every SPICE version has its pros and cons, advantages and disadvantages. The text-based is the best way to learn because it allows you precise control over every aspect of your device. Okay. LT Spice is limited to only the products that LT Spice sells, not LT Spice, that Linear Technology sells. So in their library, you only find the products that are made by them. Okay. What you need to do is you need to search for LT Spice, download it, install it on your laptops. It works on both Windows and Mac, but Mac being Mac does not have a menu interface. Also, I don't know for some why, we are stubborn and don't have a right click. So you have to enable right click by 2-finger touch. And then you can, when you do right click, and this works on both Mac and Windows, when you do the right click, it'll show you the menu options. So you can do that. But it runs on both Windows as well as Mac. No Linux, unfortunately. But LT Spice is a really great way to simulate. All these computer simulation tools are nothing but calculators. All they are doing is they are calculating. The original SPICE program is based on nodal analysis, so node equations. And so you enter your information in there and it runs its calculations. When you use resistors and you create your circuit, this is a thing you have to be careful about. This is the thing that I like to talk about. Resistors don't have polarity. But when you select a resistor in LT Spice and you place it on your in your workspace, it'll show up like this, vertically. So when you click on resistor, it'll show up as a vertical resistor. Then you click again to place it in your workspace. That resistor has a polarity, plus minus. You have to rotate it. When you rotate it, plus is here, minus is here. You rotate it a second time. And now it looks like this. And you rotate it a fourth time. And now it looks like this. So when you're placing the resistors, typically a resistor will not have polarity, right? Does not have polarity. But in LT Spice, when you pick and place resistors, you have to be cognizant of this. And you have to know which direction your current is flowing. So tie back to the previous problem where I posted the plus minus signs. If you don't place it correctly, your values will have a negative sign where it shouldn't. And the way to do this is with a keyboard shortcut, Control plus R. These keyboard shortcuts work in both Windows and Mac. Okay, so Control plus R. All right, we'll end class here today. We'll pick up here again on Friday. Review these slides, review the homework later today, sometime any other time. Put it on XX or 2X speed and just run through it. Stop and refer back to it wherever you need to, and take a crack at the homework. Okay, so if you have any questions, you can get them answered on Friday. All right, have a good day, and I'll see you on Friday. Yes. Yes, it'll be helpful for you for both this class for 145, 215, 245, 315, 345, and beyond. It's a very powerful tool. No, it's you just have to do a search for it. It's not hidden. You type in LT Spice, the first hit is download LT Spice. Just a second. Let me stop.